Hello and welcome back to Calculus 3. We are starting chapter 13, chapter on multiple integrals, integration. And the first order of business is double integrals over rectangular regions. So progression goes from 1 to 2 to 3 integrals, where they can compute area, volume, bulk, and so on. There is no limit as to how many integrals you can stack together, as many as you want. But for application purposes, 3 is enough. So I'm going to start first by looking back at Calc 1 again, where I have a function f of x over some domain, and then I pick a to b to find area. So area under this curve is going to be given by the integral, and we remember that we said that the integral is integral a to b of f of x dx, and we solve it as the antiderivative of x from a, computed from a to b, which is f of b minus f of a, which gives us the area. Now that's computed through fundamental theorem of calculus. However, if the area drops below x-axis, it becomes negative. So if I want to compute from A to B now, I have this piece C to D, which has to be calculated using absolute value, because that will give us negative number. So figuring out the area is not just computing a definite integral. You have to be careful whether the function dips below x-axis or not. So area in this case would be integral a to c of f of x dx plus the absolute value integral c to d f of x dx plus d to b f of x dx. So as you can see, there is this portion here, and I'll shade it red, which is below x-axis, and that one would create a negative area, so we take care of that term using absolute value to bump it up. The next part is, I know those of you who took Calc 2 with me, which is 10 of you right now, you know that I made a big deal about dx, because dx is the one that sets up integrals. Dx is the width of the rectangle. So when I am setting up the integrals in my head, here's the conversation that I have with myself. So say this is our function that we are considering, and we see that they intersected A and intersected B. Say that this function here is f of x, and this one is g of x. I will have my representative dx rectangle, which moves left and right. So this is what I tell to myself in my head as I'm looking at this, trying to set it up. I say area is going to be between A and B of dx. Now, top of dx rides on f of x, so f minus g. Top minus bottom. Obviously, f of x minus g of x. Now, this skill is important, obviously, for your Calc 3, because you will have a lot of those calculations coming up. So we have a setup where I said that the representative rectangle will start here being infinitely thin and zero height because it's at the point A. That's the starting point. Then it's going to swipe to the right and end here again as a point at B. So representative rectangle dx swipes all the values between A and B without interruption. Or you can think of it as we get to draw this infinitely thin representative rectangle at every point between A and B. I like to think of it as it's swiping across, but it's actually infinitely many of them stacked next to each other, filling in all of the space. All right, so what is going to happen now in Calculus 3? Well, you don't have any more representative rectangle dx. Now you have a representative French fry. Because your domain at this point, right? So let's draw. Hold on. It's not a general region. Oh, you hate French fries? I'm sorry. The answer is no. Representative asparagus, no. Yeah, it has to be a representative French fry. So what you have here is a rectangle in the domain of f of xy. So we will be integrating over this rectangle. And now you have some kind of shape on top, whatever is happening, doesn't matter. We are going to pick a representative French fry that will rise all the way to the top and take the shape on top. Now this representative French fry will have delta x and delta y sides. So if I am to draw this representative French fry here, this would be your delta x, which is dx, and this will be your delta y, which is dy. And the top of this French fry will, whatever the function does on top. So now, what we are going to do is we are going to take a whole bunch of this French fry, and we are going to fill the entire grid. So I'm holding a keyboard, right, for my surface, and you can see, imagine that each one of these keys is the base for a French fry to rest on it. So out of each key up goes a representative French fry, and on top there is the surface, which is your f of xy. So this representative French fry all of them, they go up and they hit the top of the function, filling in all the volume, right? So now, when you look at this, we have the same thing that you had for your Calc 1 using the Riemann sums, except now these Riemann sums are operating on a two-dimensional domain, which means that we have summation for x and the y. So what is the double integral definition over rectangular region R for f of x, y, and I'll call this dA? It clearly has to be the limit as delta goes to 0, I'll explain that, of the summation of f, it can't fit. Limit delta goes to 0 of the summation of f of x k star comma y k star. That's just locations of these French fries. dA, delta A. As you can see, definition for the integral is identical to what you had in Calc 1. Except now, instead of having f of x, you have f of x and y. Now, I want to talk a little bit about dimensions here. Maybe I should, let me see if I can do this. I used to have oh, there it is. Vinyl source for textbooks, so I can show these French fry things. Unfortunately, the computer is no longer showing on the projector. That will be fixed sometimes in 30 years. So here is how the shape is all fit with these representative French fry. And I want to find the better. Awesome. There we go. So you see the rectangular domain because all these guys are there. Next time you go to diner and you buy French fry, of course you're going to arrange them this way and just try to see what's going on. Right? Of course. I mean, and just hope and pray that someone will ask you what the hell you're doing, because that opens the door for you to talk about this. All right? Which is the reason why no one takes me out to eat. I just eat alone. I still make my piles, but yeah, still have. The more then what you can do is precision cut your French fries into smaller, right? Thinner. The thinner it is, the better resolution on top you get. This is a smooth surface here. Look at this ragged terrain, right? So this approximates this one, but this is with a really thick French fry. Then you cut those French fries into smaller ones. Eventually you're using spaghetti, right? And you see that already it's taking the shape of what it should be. So again, the thinner the French fry is, the better approximation you get. And you get to calculate, it's better. Now here is the definition that I just wrote. And clearly all of this consumes space, which is volume. So this double integral computes volume. So when I jump back, I will now say that volume is computed as the double integral over region R, f of xy, and then dA. Now, this dA is either dx dy or dy dx.
How important is the R?
Well, R is just denoting that we have a rectangular region, and I'll explain. You will know after the exam we'll do the 13.2, which is general regions, and we'll see how they're different. So first of all, I want to know about dimensions. I have 2 dimensions coming from dA and 1 dimension coming from a function f. So that's 3 dimensions, that's volume. So dimensionally, all of this makes sense. That's the most important part. I was wondering why it logged me out there. All right. So what should we do now? First order of business for me is to help you out. Let's say you are tutoring someone who's, 6th grade, and they are trying to figure out what is the volume for a box. So a box and they give you dimensions of the box, that this side over here is 8, and this side is 2, and this side is 4. And they memorize the equation that it's 8 times 4 times 2, which is very good. Let's say inches cubed, whatever. But this is what happened. You are a tutor now, and the kid asks you why. Let's talk. So here's why. The box sits in the xy plane with the rectangular domain 0 to 8, 0 to 2. This is your region R. So what you see here is the domain. The top of the box is a z equals 4. It's the horizontal plane, z equals 4. So z equals 4, I'll just say top plane, is also understood as f of xy is 4, because we know z is f of xy. You have all of the ingredients to explain to this kid why. Because the volume is given as the double integral of the function, and in this case that will be 4. And then you pick dx dy or dy dx, it doesn't matter. For rectangular regions, it will matter later. And this is what you say. The inner integral is a pair, and the outer integral is a pair. So now you see that the outer integral is dy. Y goes from 0 to 2, And the inner integral is dx, which goes from 0 to 8. We are going to solve the inner integral first. So we are going to solve the inner integral first. Just do the Calc 1 on it, nothing special. Copy the outside integral, 0 to 2. Integrate inside, which is 4x from 0 to 8. And you still have dy on the outside. 0 to 2. And then you have 32 here. Minus 0, who cares? And now integrate this. And there's your 64. And at this point, the kid will understand never to ask question again. Yes, so you have the inner integral. It's like layers of onion, okay? Layers of onion. And you can chain this way 15 integrals if you want to. 15. We are only going to need 3 for our calculations. So, what are we going to have? For this particular section, we are going to have a rectangular stencil cutting into whatever shape you can possibly think of, if you're able to integrate, right? So you take some kind of a shape, and you see that it's a rectangle. Squares are rectangles as well. And now you make the shape, whatever. The surface of that shape is governed by f of xy is equal to blah, blah, blah. That's z equals, right? F of x, y. So that's the surface. That is what you plug into integral. The region, if you are to take a flashlight and shine the light on top of the shape will give you on the bottom rectangular shadow, which is the domain, the region over which you are integrating. That region gives you the limits of integration, and the fxy equals blah, blah, blah is what goes inside of the integral. So you take whatever, and you take this rectangular cookie cutter stencil, right? And just keep punching into anything. As long as you're able to integrate the function on top, you will have rectangular region to set up using the integrals there. I mean, the region to give you the limits. So let's take a look at some of the problems. The first order of business is for us to learn how to compute this. So let's compute one. This is already set up. We just need to compute it. Where are those with ease? There it is. Double integral 0 to ln2 0 to 1 e to the no 6x e to the 3y dx dy. When you see a double integral or triple integral, the first integral that you must solve is the one in the middle. There's always going to be one in the middle. Now, you use your eyes to see that the integral is in respect to x, which means This is a constant. All right? Just like your partial derivatives, when you took the partial derivative in respect to y, your x's were constants. Same happens for integration. So, when I am integrating this, we have 0 to ln 2, and now I'm integrating x. So clearly 3x squared e to the 3y. E to the 3y gets copied. It's a constant. You copy 6, but then integral of x is x squared over 2. And then 2 cancels with 6 and gives us 3. So now you compute this at 1 for x, right? And we get 0 to ln 2. Plug in 1. We just have 3e to the 3y. Plug in 0 is just 0. And now you are faced with another calculus 1 integral, which is integral of e. Copy 3. Then e to the 3y over 3. Oh, convenient. From 0 to ln 2. So plug in ln 2. So this is going to be e to the 3 ln 2 minus e to the 0. 3 goes inside the ln as the exponent, so 2 cubed is 8. E and ln cancel, and we get 7. Go back. When we are faced with a double integral or triple, for that matter, the first integral you have to solve is the one in the middle, making sure you have your dx over there. Now, you integrate in respect to x. That means that y's are constant. Therefore, we copy e to the 3y because we are integrating x. Integral of x is x squared over 2. 2 cancels 6 into 3. And then we compute at 0 and 1. And we are plugging in 0 and 1 for x. So you just have to be careful and pay attention when you are doing these things. Because that 0 and 1, right, you can mistakenly plug it for y. But you have to realize that you haven't integrated in respect to y yet, so you can't plug into y. So pay attention at all times what you're doing. Try to focus, because most of this stuff is just really picky. It's very easy. As you can see, you are doing 2 Calc 1 integrals nested. Just be careful. Yeah.
So as long as the integral and the dx or dy match, it doesn't matter what order. Like you could have written that integral from 0 to 1, integral from 0 to ln of 2, 6x e to 3y, dy dx.
That only works for rectangular regions. It doesn't work in the next section where you will have to change this if you want to swap order of integration. Yeah. So right now, what you said, yes, you can swap order of integration, but the next section, that goes out a window. So we'll get there. All right. The next order of business is for you to set up the problem. This is problem 18 in the textbook. They just give you all of the information, and they just ask you to set up the limits and compute. Now here's your rectangular region R, given as all of the set of points x, y, such that, this is 18, So 1 less equal than x less equal to 2. And -1 less equal than y less equal than 1. So I will suggest you to draw the region and then set it up. So I will start by drawing the region. I have one and two on x-axis, and then I have +1 and -1. So here is the rectangular region. R. As I am setting up the integral, obviously x squared plus xy stays, And now I have the choice whether I want to put dx dy or dy dx. It really doesn't matter. Let's go with dy dx, because we can. The outer integral needs to match dx. You can see that dx goes from 1 to 2. Because if you are to draw dx, it slides from the left to right. It starts at 1 and ends at 2. You can also see that here. The next order of business is to talk about the y. So the inner integral now, which is y. Y is the horizontal representative rectangle like that. And that one moves clearly from -1 to 1. So there's our setup. Solve the inner integral first. We are integrating in respect to y. So I have x squared y plus xy squared over 2 computed from -1 to 1. Plug in 1 for every y. We get x squared plus x over 2. Now plug in -1, and remember that we are subtracting, so plus another x squared and minus x over 2. So now we are left with 2x squared, which is 2/3 x cubed from 1 to 2. That's 2/3, 8 minus 1, so 14/3, if I calculated all this correctly. Your Mathematica is going to calculate these. You will just say integrate, type in the function, and then you will write dx dy or dy dx. That's when you type that dx dy or dy dx, you have to type that in the correct order, and then say from. You will get this problem solved. So practice Mathematica input. Yes. Well, for this particular, next question addresses that. But for this particular problem and all of the problems that we did before, it doesn't matter. Because you're solving the problem, and they can be interchanged because it's a rectangular region where all the limits are constants. You will see after the exam we are going to cover 13.2 on general regions. You will have functions and limits. And you will have to obey certain rules for the whole thing to be computable. So right now, why did I pick to integrate y first? Because there was only one y. I didn't want to integrate both x's. But then it doesn't really matter because we picked up y in both and then calculate. It doesn't matter. It really doesn't matter. Let's see if it's going to matter on the next example. Integral over rectangular region, xy sine x squared dA, and the region is given as all xy such that x is between 0 and square root of pi over 2, and y is between 0 and 1. I hope you're working on this stuff, trying to figure out which one. Try to do it both ways. Try to do dx dy and then dy dx. See, do it.
Yeah, it does go to 0.
Does it matter which one you integrate first?
Yeah, kind of. If you integrate it by y first, it makes things easier, right?
So if you do dy dx, you will integrate y first, and that will become a number, and then you can just do u sub after that, or you can do u sub and just drag y. So visually, it's just easier if you do dy dx, but you are not gaining anything. We'll see that for certain problems you will have to do one thing or the other, but let's just quickly write this one. And we'll solve one more problem after this and then do the review. So I will set this as dy dx. So our outer is x, which means 0 and square root of pi over 2, and the inner is y, which means 0 to 1. When I integrate, don't forget to copy the outer. We get y squared over 2, and then x sine x squared is a constant. Computed from 0 to 1. When you plug in 1, you get 1/2. And you plug in 0, everything dies. And now you use u sub. All right, so 0 is 0. And when you plug in square root of pi over 2, it becomes pi over 2. Awesome. We have 1/2. I need a 2 there, so it's going to be a 1/4 here. Sine u du. Awesome. Integral sine is negative cosine, so negative 1/4 cosine u from 0 to pi over 2. When you plug in pi over 2, you get 0 times 1, and we get 1/4.
If you went the other way, it's impossible.
Yeah.
There's only one way to do it here.
You can do both ways.
Oh.
Fine. No, it's just visually it's easier this way. So the last problem for this section is the double integral r y cubed sine xy squared dA where region R is given as 0 less equal than 2. All right, so that's it.
Do you want me to remind you to give the test to the learning center tomorrow so she can take it?
Oh, that's tomorrow?
That's what she told me.
Oh yeah, I forgot about that. I completely forgot about that. Good. So yeah, so I'll be in school at 5. So I'll text her, tell her to come to my office at like 5:20, 5:30.
That's fine, 5:30.
Yeah.
Go to your office.
Yeah, that's when I'm gonna be in, and then we can go down for the test.
Okay.
All right.
See you.
Yeah. Because I have a meeting at 5:30, so. So which order are we using here? Can we do the y dx?
No, maybe.
Why not? It's only gonna be, yeah, 3 integration by parts, nothing to worry about. No? All right. So x is the inner and y is the outer. So let's see what we get. As I integrate x now, y is a constant, so I copy y cubed. Integral of sine is negative cosine xy squared, and the y squared comes out. You see that? It comes out as a constant, and then, right? You don't have to do integration by parts now. So we have negative y cosine you have to be very careful here. Cosine of 0 is 1, exactly. So this limit has to be computed. So when you plug in 2, you have negative y cosine of 2y squared, and then minus, and the minus make a plus 1. That's what I said. Please pay attention. dy. There we go. Nice. So now we use u sub over here. So the whole integral, when I plug in 0, it stays 0. When I plug in root that is just pi. And then it becomes negative 1/4 cosine u du plus, this is just going to be y squared over 2, so 1/2 y squared computed from 0 to root pi over 2. Awesome. So one integral I substituted, the other just a y I integrated using the old limits. So now integration of this is sine, so negative 1/4 sine u from 0 to pi. They all die in sine, so that's all done. This is plus 1/2 of pi over 2, and that's pi over 4. Is that what you have? Pi over 4? Yay! So to set up the integral, order doesn't matter unless the function inside cannot be integrated with the order that you chose. Then just swap them. And the beautiful thing about swapping the order for the rectangular regions is you just get to swap the dx dy, and you get to swap the limits in front, right? Because they have to match y with y and x with x. And that's it. Now the headache is the next section, where you have general regions, which introduces functions in the limits, and on the outer you will have to have numbers to end up with, let's say, pi over 4, and you are only allowed to have functions on the inner side. So that's going to be fun, but that's after the exam. So let's talk about the exam next section. So take a few minutes and then we'll talk about the exam. Bye, stream.